So let's go back to the examples. And in fact, there was a question before the break by Ahmed. What happens if the red one is at the form? What does the yellow report? In fact, this is the next example. It happens to be the next example, which is exactly this, which is what a coincidence. So I'm asking the same question. Suppose that we have the question mark here, so what's a reasonable answer here? And now it's not so easy anymore, because the question is whether it should report true or false, which one is reasonable. Now, we have a red thread, which is adding a 7, in the process of adding a 7, and we have a yellow thread, which is true, it started after the add, but ultimately it's trying to check whether the 7 is there or not. So let's first take the first scenario where the answer is true. Is this reasonable? Well, according to the definition I will give you later, yes, it's a reasonable behavior. And why is that? The idea is that because the add 7 and the contain 7, they overlap in time, it can be the case that the red thread succeeded in physically adding a new cell in the linked list, if it was a linked list, or it succeeded in changing the state of the data structure, so that when at the point where contain looks at the list or at the data structure, it does find the 7 there inside the set, and then it reports true back to the caller. So this is a reasonable behavior of a concurrent program that implements a list or a set. But now what happens if you go back to the question mark and now I ask false? Is this a reasonable behavior? Now, the surprising thing is here is that, in fact, this indeed is also a reasonable behavior. Why is that? Because, again, because these operations overlap in time, it might happen that although the contain starts after the add, the contain may take effect before the add takes effect. Where take effect is something, or takes effect something that we will define formally later, or formally, we will define precisely later. So indeed, this is also a possible reasonable behavior of a concurrent set. So in this case, the contain can answer both true or false. So this means that you have two possible correct behaviors of the concurrent set in this case. And in general, what we will say is that the only thing that you can say unambiguously about the behavior of a concurrent data structure is that if you have operations that do not overlap in time, then you have a predefined output value. I mean, the behavior is well defined, it's deterministic. If you have overlapping operations, then as we will see, then because they are overlapping, any possible interleaving of the answers is approved, it's fine. So in this case, in fact, if you implement a program and your program always says false, in this case, it's fine. If it always says true, it's fine. If it says true or false, depending on the situation, it's also fine. And this will make more precise later. So this is one of the essential messages that you have to take with you today. Is that overlapping operations have non-deterministic behaviors. We will make this more clear through more examples. Now let's take an even more complicated or illustrative example. You have three operations by three threads, the red, the yellow, and the blue, that are doing contain, add, remove on the same element, and all of which are overlapping. So all three operations, you see that all three calls are overlapping. It's true that the add starts first, the remove starts second, and the contain starts last. but the interleavings are not clear in which order these operations take effect. So let's see at the possible scenarios and which one of them is reasonable. So now I have put 2 question marks, and I will instantiate these question marks by true and false respectively. We get 4 combinations, and we see which combination, which scenario is reasonable and which one is not. So let's start with the scenario where both are true. So is this a reasonable scenario? So you can think about this a bit, 10 seconds, and see what you conclude. I mean, usually in the class we do it together, but it will be difficult here. So you can just think in parallel if you wish. We are talking about concurrency, so concurrent thinking. So you have add, remove, and contain. And all operations are successful. Is this reasonable? And the answer is yes. So what's a possible scenario in which this happens is that the add 2 will take effect first. So 2 will be added conceptually to the set, after which the contain takes effect, and it finds the 2 indeed inside the set. And last, the remove will take effect, and it finds the two inside the set, and it removes it. So all 3 operations, according to this interleaving, are successful. So the true is fine. It's a reasonable behavior. So what about the true and false? So this means that the contain fails, but the remove succeeds and the add succeeds. Well, this is also reasonable. Why is that? Because maybe, I mean, there are 2 possible scenarios in which this can happen. First, if the contain takes effect first, it looks at the set, there is no 2 inside. So it says false, fine. After which the add takes effect. So the 2 is inside the set now. After which the remove takes effect. It finds the 2 inside the set and it removes it. So that's one scenario in which the contain will fail and the remove will succeed. Another scenario is that the add will take effect first, the remove will take effect second, so it successfully removes the 2, after which the contain doesn't find the 2 inside the set because it has been removed by the yellow thread, and therefore it says false. So in fact, this is a reasonable outcome, because we have 2 scenarios that are witnesses to the answer given here, true or false, respectively. So any questions up to now? So it's important that you understand this concept, this way of reasoning, because we will make, okay, so we will make it more concrete later, but I just want you to get the flavor of this at the moment. So now let's take false and true. So the remove will fail. The contain succeeds. In fact, this is also reasonable. Why? Because, for instance, the remove can take effect first, so it cannot find the 2 to remove it, so it's false. After which the red thread will put the 2 inside, and then the contain will find the 2 there. And how this can happen in a concurrent implementation of a set, we will find later. I mean, this is when you implement the set algorithms, you see that these scenarios can happen. So this is, again, reasonable by the reasoning that I gave. Take effect here first, remove, false, and then add 2, and then remove 2. Finally, we take the case where both these operations fail. Again, this is fine because both the yellow and the blue can perform their operations in any order before the red. So the remove will fail because it does not find the 2 inside the set. The contain will fail because there is no 2 inside the set, after which the red will add the 2 successfully to the set. So you see that in this case, all 4 combinations of these answers were possible. So if I put a false here, what will happen? In fact, if I put a false here, then this is not a reasonable behavior because add should always succeed unless there is a 2 inside the set before. And because it's the only operation which adds a 2 to the set, and assuming that the set is initially empty or does not contain a 2, then this operation should always succeed. So if you put a false here, it's not a reasonable behavior. So you see that although in concurrency you will get a lot of behaviors that are approved, that are okay, there are behaviors that are not okay. For instance, if I put add 2 and then false here. So and we'll define precisely later, either today if I have time or in the next lecture, what we mean exactly by having a reasonable behavior or a behavior being reasonable. Yeah, so this is fine. So let's look at some more examples for queues. Is this a reasonable behavior? So first we in Q2 and the call terminates. In Q7, the call terminates and then the Q2. In fact, this is a sequential history, so there is nothing dramatic here. Where although it's a concurrent history in general, so you see that sequential histories are special cases of concurrent histories in which each response follows immediately the corresponding invoke. So the invoke is followed immediately by respond, invoke, respond, invoke, respond. So this is a sequential history. And this is fine because in Q2, in Q7, and then in the Q2, fine. So if you try to do Q7, this is not a reasonable behavior because any reasonable implementation of a queue, it enqueues 2 first because this terminates and then it enqueues 7 after. So you see that if you have calls that do not overlap, then the sequencing is important, the order is important. And this is exactly what we will capture in this notion of linearizability. So in linearizability, we'll say that concurrent calls, they can come in any order, but calls that are not concurrent are taken in the order in which they occur. So in this case, the order of these 3 operations is well defined, is unique. This first, this second, and this third, and there are no other possibilities. And because this is not a possible behavior of a queue, then this is not approved. How about this one? What can I put here? So you have 3 now. We take the same operations as before, but now I make them overlap. So now things change dramatically. So for instance, what will be the value of the question mark here? So can it be 2? Yes, it can, because the enqueue2 may take effect before the enqueue3 and before the dequeue2, which means that enqueue, enqueue, and then dequeue2 first. How about dequeue3? This is also reasonable behavior because the enqueue3 may take effect first, followed by enqueue2, and then dequeue3. Or enqueue3, dequeue3, enqueue2. So this is approved behavior because there are, in fact, indeed several scenarios which induce this outcome, the 3. Either we enqueue3 before enqueue2, and then we take a dequeue, or enqueue3, dequeue, and then enqueue. So all these give you same outcome, which is indeed the behavior of a queue. And as we will define later, the behavior of a concurrent implementation of a queue. How about the 4 there? Now, although these methods are overlapping, this is not a good behavior of a queue. So you see that even if calls overlap, it's not always the case that you approve all their interleavings, because here, obviously, this is not the behavior of a queue because you never enqueue a 4. So you never put a 4 inside the queue, so you should not be able to dequeue a 4. So this should give you this. How about this one? It's more difficult, let me see. So if you have a 3 here, is it possible? You can think about this. So you see that the blue thread is overlapping with both red and blue. No, so what I'm saying, the blue thread is overlapping with both red and yellow. So I think this is not an allowed behavior, because in any case, you know that the 3 will be enqueued after the 2, because this operation, these two operations, they do not overlap, so their order is well defined. The 2 is enqueued before the 3, and a DQ cannot fetch a 3 first before it has fetched the 2. Okay. So now, if I put a 2 here, then certainly this is fine, because this may take effect first, and then this may take effect, and this may take effect. Or this takes effect first, and then this takes effect, and then this takes effect. If I put a star here, then this is also possible, because the DQ may take effect before the enqueue here. In any case, this is a possible outcome. How about this one here? So you see that things get more and more complicated. So here, this is fine, because all these operations here are in queues. And here we have DQ, DQ. So these two operations overlap. So this means that you can DQ in any order, but you should DQ a 2 and a 4, or a 4 followed by a 2. And so DQ2 followed by DQing 4 is possible, because you can enqueue 2 and then enqueue 4. So this takes effect, and then this takes effect, and then this takes effect, and this takes effect, and then this takes effect, and this takes effect. 4 followed by 2, this takes effect first, so you have 4 in the first in the queue, and then followed by 2, followed by 7, followed by another 2. So you can DQ 4 and then DQ 2. So this is fine. Okay, so now we have seen examples, and now, so can you please mute your mics, because we hear a sound in the background. So it would be good if you could mute the mic. Unless you have a question, you're very welcome to unmute. Oh, yeah, no, this was out. Nice. Anyway, so now we have defined the notion of concurrent histories. We have given a flavor of what we mean by reasonable behavior. Let's try to make these notions more precise. And we do that by defining the notion of linearizability, which will be the notion of correctness for concurrent data structures. And in fact, this is the notion of correctness, for concurrent data structures. So what's linearizability? Let's try to define this concept step by step and try to use it to explain the possible or the scenarios that we have gone through. So linearizability is an operation that you perform on a concurrent history H, the result of which is a sequential history. So how do we define this linearization operation? So we do it in different steps. So first we define an ordering on calls. And as I told you, this ordering on calls reflects the order in which occur, meaning that overlapping calls, they are not ordered, while calls that do not overlap, they are ordered. So this ordering definition, if you are familiar with algebra, is a pre-order, which means that some elements may be equivalent, and then you have the partial order on the equivalence classes, but this is not something that you need to understand in this course. What I can say here is that this ordering is defined in two parts. First, you have a precedence, where a precedence between two calls means that, as I told you, that one call occurs before the other. So call 1 precedes call 2, if call 1 ends before call 2 starts, which means that the interval of call 1 precedes the interval of call 2. This is exactly what I told you before in the examples. So the precedence, again, in a concurrent history, you relate the calls inside. So you have all these calls inside this concurrent history. Now, some of them are related by this precedence ordering. So for instance, these two guys are related by the precedence ordering. The green call precedes the red call, because the green call ends before the red call starts, or the interval of this call precedes fully the interval of this call. And please interrupt me if there are any questions. So I would like you to answer or to understand this during the lecture. And also, this call precedes this call, the blue one here, because this call ends before this one starts. So this is the precedence relation on the calls, the set of calls inside the concurrent history. Overlapping means that the calls overlap. So this means that the call 1 and call 2 are overlapping if their intervals overlap. So for instance, this one overlaps with this one because you see that none of them ends before the other one starts. So they are overlapping. And these two are also overlapping. Okay, so this is, sorry, the overlapping text disappeared, but doesn't matter. But okay, so anyway, what I wanted to say is that if you look at the concurrent history, let's go back. Oops, sorry. We have the precedence. Here, sorry, let me go back to the same place. And then you have the overlapping. So these are the two concepts. Some calls precede some other calls. This one precedes this one, and some overlap. So now the notion of linearizability will order the calls that precede each other accordingly, and it has an arbitrary ordering on the overlapping calls. So, okay. So now knowing that, we go back to our concurrent history H, and we define what we call linearization points, and this is important. So now what we do is that we will try to make this notion of taking effect more concrete. So the intuition is that when you implement a data structure concurrently, each invocation of a method will take place at some point during the execution of the program. And it takes place between 2 points, which are the invocation and the response points of the call. So we will try to make this more concrete by this definition, which you call linearization points. So if you give me a concurrent history H, then for each call, I take one arbitrary point inside the interval of that call. And I call it the linearization point for that call. So for instance, it's a point inside each call. So the important thing is that you take the point between or the interval of the call. So for instance, for the green one, I take the linearization point to be there. I am free to choose my linearization points. And for the red one, I take my linearization point to be there. For this yellow one, I take my linearization point to be there. For the blue one, the same thing. For the next red one, and for the next yellow one. So for each call, I am defining somehow, I'm guessing if you wish at the moment, the point of time at which this method takes effect. This is, for instance, the add2. This is a point where the add2 will be added to the list or to the set. This is the point after which, if another thread comes and looks at the data structure, then it sees the 2 there. And before that, it doesn't see the 2. So it's exactly the point in the program where, or in the execution of the program, where the method takes effect. It will be visible to the other threads. So the only requirement we have is that each linearization point is defined within the interval of the call. And this has a nice consequence. In fact, 2 nice consequences. First of all, if you have one call which precedes another, for instance, the green one here and the red one here, then you know that the green linearization point will occur before the red, because these 2 methods, they do not overlap. So this ends before this one starts. So wherever you put the linearization point for the green guy, it will be before the linearization point of the red guy, wherever you put the red point here. I hope this is clear. Yes, a question here. Shouldn't the point for at 7 be after? No, you are at 7. Should be after what? Contain 4. No. It's up to you. So according to the definition of linearization point, you put it anywhere in the interval. What I was about to say is that, so one nice consequence of this definition of linearization points is that if you have one method preceding another one, then wherever you choose to put the linearization point for one of them and the other, because they do not overlap, the linearization point of the preceding call will occur before the linearization point of the subsequent call, of the following call. So I hope this is clear. The second thing is that if two calls are overlapping, then because I'm free to define their linearization points, then I can choose them to take effect in any order, because by just, as you'll see, later I will put this green point after the red point, and then I reverse the order in which I observe these calls, in which these calls take effect. So anyway, this is the linearization points. Just pick a point in the interval of the call. And the nice property is that if one method call precedes another one, then its linearization point will be before the other. By definition, if two methods calls overlap, then again, by definition, because you are free to select the position of the linearization points, provided that you are inside the interval, then you can play with the order of these concurrent calls. So this is the first step in the definition of linearization of a concurrent history. Remember, I told you ultimately from such a linearization operation and a concurrent history, I'll obtain a sequential history. But we are not there yet. This was the first step. The second step is that I define the linearization operation. So again, give me my concurrent history H. So the linearization operation consists of different steps. First, define the linearization points. So as I told you, this is what we did in the previous slide. Just put the linearization points as you like. So this is one choice. I choose to put my linearization points like this. This is the first step. We know what this means. Just put linearization points. And then consider the order of the linearization points. In fact, the order of the linearization points gives you the order of the method calls seen as a sequential execution. Let's see what this means. So let's order the linearization points according to their order. So this is the first one, because this is the one that occurs first, before all the other linearization points. This is the second one. This is the third one. This is the fourth one, fifth one, and sixth one. So you see that the order in which you do this or put your linearization points, it has nothing to do with the relative order of the start and end of the different calls, only provided that you put the linearization points inside the respective intervals. So by definition, this point will always be before this point and always before this point, while these two can be interchanged. So this was the second step. I chose my linearization points. Second, I enumerated them according to their order in which they occur. Order the calls accordingly. So this means that I take now each call and I generate the corresponding call in that order. So this means that first I take the green call here, which is the first one, and I extract this call. I take it out from the concurrent history. So now I have, interesting, I have a call in which the response comes directly after the invocation. Now take the next one, number 2. Take the corresponding call again at 7 true and put it after. So you see that I'm ordering the calls according to the ordering of the linearization points. And you see what I am doing here. I am in fact generating a sequential history, because if I apply this operation, I am taking these concurrent calls and I make them sequential. I take my concurrent history H, I'm generating a sequential history. And this sequential history is derived, in fact, it's unique by the given concurrent history together with the order of the linearization points that I have defined here. So I take number 3 here, which is the contain 4 and false by the yellow thread. I take the 4th one here, which is the remove 2 true by the blue thread. I take the 5th one, which is here, which gives me add 7 and false by the yellow thread. And then finally, I take the 6th one, which is the remove 2 false by the red. And the thing which is interesting also here is that you see that because the calls by the same thread do not overlap, I keep the order in which calls I perform by each given thread. And this reflects the fact that threads are indeed sequential by themselves. So each thread by itself is a sequential program, but we have concurrent sequential processes executing. Okay, so this is very nice because I took my concurrent history and I chose my linearization points, and in such a way I obtained a new history here, which is sequential. And I call it H prime. And this H prime is sequential by definition because I take each call before I take the next one. And now we say that H prime is in the set of this is a spelling mistake. Maybe I should not do it now, but okay. Sequential history. So now I say that H prime is a set of linearizations of H. So this means that each history has a set of linearizations. Each one of them I get by defining an order on the calls, which is induced by some definition of the linearization points. So in fact, indeed, each concurrent history has a finite set of linearizations, each one of which I get by a possible ordering of the linearization points in the manner that I defined. So to summarize up to now, we have a concurrent history, we define the linearization points, I collect methods sequentially one after one according to the orders or the order of the linearization points. I take the output, which is sequential history H prime, and I call it a linearization of H. So if you are familiar again with algebra, this corresponds to a linearization. This means that you have a pre-order and from this, or partial order, and from which you induce a total order. Okay, so now the interesting thing is that, as I told you, if methods overlap, then you can choose their linearization points in the order in which you like. So for instance, I could have chosen the linearization points of red and green in the reverse order. So this means that I could have done this. So now the red will be first and the green will be second. So now when I take its linearization, now I generate a new linearization of the same history H, and I do that by making the sequential history again reflect the order of the linearization points. So this means that the red now should come before the green, like this. So now I obtained a new history H double prime, which again is a sequential history, which again, okay, so this will be H double prime, and linearization. So I will correct these things before I upload the slides. I'm sorry. So in fact, the slide I did yesterday and I checked, but it's hard to see all the details. But please, if you detect any typos in the slides or mistakes, then don't hesitate to tell me. It's very much possible that I make mistakes because it's quite overwhelming to do these slides, in fact. Anyway, so by this, I will not correct it. So this is H double prime is again a linearization of H. So the message to take from here is that, in summary, that if you have a concurrent history, you can reorder concurrent calls, but not calls that precede each other. So now we go back to the original history, which was H prime, which is again in the set of linearizations of H, the sequential history. So let's look at some of its properties. Call one, for any two calls, call one and call two. Call one precedes call two in H, implies that call one precedes call two in H prime. So, and this is what we saw. If this precedes this in H, then the same thing will happen in the result. So for instance, this one and this one, they are related by the precedence relation. Always, however you define your linearization points, if you compare the corresponding calls in the sequential history, they are in the same order. But the overlapping ones, they can come in any order. So this is an important property. If call one precedes call two in H, call one will precede call two in H prime. And this is by the way we have defined our linearization points. Okay, so now, on the other hand, if calls are overlapping, as we saw, then we can choose how we order them, as we saw before. So this will not apply. So this applies only if it is the case that the calls precede each other. So precedence gives you precedence in the sequential history. Overlapping does not imply anything. So this is the case with linearization of graphs, for instance, if you have studied algorithms and data structures. So, linearization of DAGs, which is what you have here in some sense. Okay. So, any questions up to now? So now, again, let's go back to our history H. Now we have defined its linearization, H prime. So now we go one step further, in fact. So you see what I told you in the beginning, you have this hierarchy of abstractions. So what we said, what I promised you from the beginning was that we will go from concurrent histories all the way down to abstract data types. And now you will see evidence of that. So from concurrent histories, we know how to go down to sequential histories by defining linearization points. And now, if I have a sequential history, I know how to go to a data type. I simply take and collapse decals and make them atomic operations, and in such a way obtain a trace of H prime, which be a trace of the concurrent program now. So from concurrent programs, from concurrent histories, sequential histories, to traces, to abstract data types, from overlapping concurrent calls to sequential calls, and then to atomic operations. And we know how to do this. We take each call and collapse it into one operation as usual. So this will be add 2 true, add 7 true, contain 4 false. So everything now ties together like this. So in such a way, from the concurrent history, I obtain the sequential history, and from it, I obtain the trace, tau, where tau is the trace of H prime. So now, tau is in the set of traces of set. In fact, because I'm adding 2, adding 7, containing 4 is not true, it's false. Remove 2 successfully, add 7 unsuccessfully, and remove 2 unsuccessfully because I have already removed it. So this is indeed tau is in the set of traces of a set. And now you know that because tau is in the set of traces of a set, and tau is the trace of H prime, so H prime is in the set of histories of a set, as we said already in the previous lecture and earlier today. So these 2 guys together will give me the fact that H prime is in the set of histories of a set. And now I say that because H prime is in the set of histories of set, and H prime is a linearization of H, then these 2 guys will tell me what I call that H is linearizable with respect to the abstract data type set. And this is the definition of linearizability. So concurrent history is linearizable with respect to an abstract data type if there is a way to linearize it, if there is a way to define linearization points such that the obtained sequential history is a history of the abstract data type. And being a history of the abstract data type means that if you transform it to the unique trace of the history, then the trace is in the definition of the abstract data type. So now this gives a nice picture of our, if you wish, semantics and our safety properties, because later I will call a concurrent program, I will say that it satisfies the specifications of implementing a set if all its histories are linearizable with respect to the abstract data type. This will come later. So at the moment, what I would like you to understand is that if you give me a concurrent history, I can linearize it, and then I compute its trace, derive its trace, and then I check whether its trace satisfies the given abstract data type. And if this is the case, I call this history linearizable. And in fact, this explains all the decisions that we made before in the examples. I will just give you 1 or 2 of these examples. For instance, this history, we said that it respected the specification of being a set. And why? Because, no, in fact, in general, so just to summarize this lecture, what I say is that if you give me a concurrent history H, in the first step, I take a concurrent history. So what we did in this lecture, in the first step, we took a concurrent history H. We defined linearization points for the concurrent history. In the second step, I defined the sequential history, which was defined by the concurrent history in addition to the linearization point. So I got H prime, which was a sequential history, linearization of H. Sorry, H prime is linearization of H. And in the third step, I defined the trace of the sequential history, and I concluded that this is indeed the trace of a set. And this told me that this H prime is in the set of histories of a set. And these 2 guys told me together that H was linearizable with respect to a set. So you see that the opacity here is small, and this tells a story. So this means that if you want to remember one thing from this lecture, we translate reasoning in the concurrent setting to reasoning in the sequential setting. And this is very important because it makes life much easier. We know what something is correct in the sequential setting. We all of us are very used to the sequential setting. We are new to the concurrent setting. It's hard to reason in the concurrent setting, but this is one instance of some elegant framework that allows you to translate reasoning in the context of concurrent system, translated into reasoning in the context of sequential systems. And this is very systematic, and we will see applications of that throughout the course. So we'll generate or we'll consider concurrent algorithms, but to reason about their correctness, which is not easy, we will translate their correctness into sequential correctness. But this translation, how to check it for a given program, is difficult. In fact, we have a PhD thesis to be defended, hopefully soon, of a student who has spent several years on designing algorithms that look statically as some concurrent programs, and check automatically whether such a program satisfies some abstract data type or not. And all this done is done automatically. And this gives rise to very complicated reasonings and algorithms, but this will be on this course. So the thing I want you remember from this lecture is translate concurrency to sequential or concurrent behavior to sequential behavior. In such a way, you get many things for free, at least conceptual. Okay, any questions? No? Okay, so then next thing is that I will give you the assignment either later today or tomorrow. And you'll have around 2 weeks deadline. And then there is a lab on Friday. And please remember that the lab is on Friday. And don't panic, because some people panicked last week because they, after all, they came to the lecture, which was canceled. And they thought it was a lab. And then they were urgently asking for links, etc. So just keep in mind that I will tell you if a lecture is canceled. I'll tell you in the lecture before, and I also send mail through Student Portalen. So thank you very much and see you. So on Friday, the lab will be given, I think it's on Friday, by Sarvajit. So see you next week then. Yes, there is a question. Let's see what the question is. Ah, thank you. Thank you very much. Thank you. Okay. See you. Bye. Ah, this is, I forgot this. In the step one, the choice of the linearization point has large freedom. Is it possible to choose a history that's valid for all traces? So, Albert, I don't understand. I understand only invalid. Yeah, so if you choose your linearization points wrongly, then you get a sequential history which does not satisfy the specification. But the linearizability tells you that, okay, so you should find one linearization which is correct. And in fact, if you are designing a new data structure, concurrent data structure, if you look at papers that, because it's a research topic still, it's hot. Still how to come up with good algorithms that implement these data structures is still a hot topic, especially if you have more complicated data structures like hash tables, skip lists, and things like that. Then the authors are also asked with the algorithm to provide the linearization policy, a witness that tells that their algorithm is linearizable. Yeah, so yes, so now I understand the question because you wrote valid. I didn't understand invalid. Yes, if you are not, if you define your linearization points wrongly, then it will be, you may violate the specification, but this does not imply that the concurrent history does not satisfy the specification. So the concurrent history satisfies the specification if and only if there is at least one linearization of the concurrent history that satisfies the specification. So I hope I answered your question. Yes, thank you. Any other questions? Okay, then see you next week. Thank you.